See, I'm not flexing, but while working over a decade in industry as a mechanical design engineer, I have reached a point in my career where I just looking at the mechanical parts, I can clearly tell whether it's designed by a beginner design engineer or an experienced mechanical design engineer. And here I'm not talking about GD&T, tolerance, fits, or any advanced technical skills. I'm only talking about the geometry of the part, the pure design thinking behind the part. That how you design a part, how you designing a part from completely scratch. What I observed is many mechanical engineers, even after several years of experience, still lack in practical exposure to manufacturing and assembly processes. And because of that, their design thinking do not develop beyond the CAD software. They can design but only for the function, just enough to work on a screen. And that may be acceptable for concept design, for sales and marketing visual presentation, for 3D printed prototyping. But the moment the design goes in actual manufacturing, a lots of problems start showing up in manufacturability. Sometimes it becomes nightmare for machinists, and eventually it leads to much higher cost. And this is what creates a clear difference between a CAD engineer and a well-experienced design engineer. An experienced mechanical engineer with real practical exposure, they does not just design to fulfill the function, unlike a CAD engineer. They actually design for manufacturing. They design for assembly. Last but not least, they design for strength and rigidity. And this is exactly what we are going to learn in this video. And please excuse me for my voice today. So the first and foremost is designed for manufacturing. In industry, we often call it DFM. It simply means your design part must be optimized for manufacturing. But the problem is most of engineers approach this in a very wrong way. Instead of designing for manufacturing, they actually try to adjust the manufacturing for the design. What does mean is first you understand the functional requirement of any design. Then you roughly design the parts in CAD. And then you try to apply DFM, try to optimize the design for manufacturing. It sounds simple, but in reality, it often leads to complete redesigning of the part or either compromising in function. For example, you need to design a sensor mounting bracket with height adjustment feature. So you designed a bracket with adjustment slot in sheet metal because sheet metal brackets are very common for sensors. Now you go for DFM review and you realize that for 200mm bracket height, 2-3 mm sheet metal thickness is not stable enough. So you try to increase the thickness 6 to 8mm and now you are stuck. Because if you increase the thickness 6 to 8mm, the sheet metal cutting and bending will not be easy. As a result, bracket shape may not come out properly, even though it looks proper in CAD. So to solve this problem properly, you may need to shift to machining process instead of sheet metal process. But then you have to redesign the complete part, create multiple parts, all the boltings, and then assemble it with the bolts. And that's the real pain for any mechanical engineers because it becomes time consuming and very frustrating. And in real projects with deadlines, you rarely consider to redesigning the part. So instead you start compromising and eventually leads to a poor design. So what is the correct approach? How to design for manufacturing? So before starting any design in CAD, first step is you need to understand the functional requirement at much deeper level so that you can first decide the manufacturing process for the part you are going to design. And then you design the part for the function within limitation, capabilities and tolerances of the selected manufacturing process. Confusing, isn't it? So take the same example. Here, you should not start the designing of sensor bracket until you fully understand the functional requirement and decide one manufacturing process. In this case, one of the functional requirement is bracket height. If the bracket height is within 100mm, you can choose sheet metal and you designed it in sheet metal module. with 2 or 3 millimeter thickness of sheet, easy to manufacture and very economical. But if bracket height is going to be more than 200-300 millimeter, you should already decide to go with machining and then you design the part accordingly. But if the adjustment requirement is too high, let's say more than 20 millimeter, then instead of focusing sheet metal or plates, you can shift the concept completely for something like shaft and clamping brackets, far better than in adjustment. You can locate the sensor at any height. And that's the key. First, understand the functional requirement at much deeper level so that you can decide a manufacturing process for that part and then design that part for that manufacturing process. That's the design for manufacturing. But the problem is there are multiple manufacturing processes. Sometimes it's sheet metal, sometimes machining, injection molding, and even 3D printing for prototypes. But in real projects, it becomes a problem because for each manufacturing process, you need to find a different vendors, coordinate with them, manage quality, timelines, and it becomes messy very quickly. And this is exactly where Rapiddirect comes in. Rapiddirect is digital manufacturing platform where you can get CNC machining, injection molding, sheet metal fabrication, 3D printing, die casting, vacuum casting, EDM all in one place. Let me show you something very practical. You just upload the CAD file in their platform, select material and process, and you instantly get a quotation. So instead going back and forth with different vendors, you can directly evaluate the cost in minute. And this is actually useful when you are doing the DFM because before even you place an order, the platform automatically generates a DFM report. It tells you what exactly which part of design need to be modified for actual production, helping you to avoid costly rework. So if you want to try this out, check out the link in video description and bring your design to the life with Rapiddirect, CNC machining, 3D printing, and sheet metal fabrication. With my link, you can also get up to 20% off on your first order. Now let's back to the video and let me take another example. Say you have to design a non-rotary rectangular slider. So before starting any design in CAD, first we need to understand the details at much deeper level. Like what level of precision is required? What would be the guiding length? If the precision requirement is not much high, let's say it's a loose running fit of around 50 to 100 micron, you can choose a milling process. And design the part for milling process means you must avoid the sharp internal corners because milling tools are round. So sharp corners are not possible. So either you can add internal flits and chamfer on mating rail, or you can provide undercut at the corners. Yes, these options reduce the contact area slightly, but for a loose running fit, both options works fine. But if your requirement is precision close running fit, let's say in range of 5-10 micron, you must select a process like wide EDM. In that case, you can keep the sharp internal corners with a minimal flit on the rail edge, and it works fine. Now you might say that Ayush, as you are saying that design your start based on the manufacturing after selecting the manufacturing process. Does that means DFM is not required later? So answer is no, DFM is still essential, but not to decide the manufacturing process. If you're deciding the manufacturing process later or changing the manufacturing process, for a designer it leads to redesigning the part, or maybe they will start compromising in function, as we have seen in earlier example. And this can be completely avoided by just fully understand the functional requirement and then decide the manufacturing process first and then start designing. Because once your manufacturing process is clear, half of your design and the tolerance decisions become straightforward. And then DFM is used only for further optimization, like tolerance relaxation, tolerance stack-up analysis, and GD&T refinement. Next is design for assembly or DFA. Let's take a simple example. You design a motor mounting plate. Functionally, you can design it in this way, where the threaded holes are in plate and bolted head comes below the base plate. From a design and manufacturing point of view, this is completely fine. But from assembly point of view, it becomes problem. You may somehow assemble it for first time, but later for maintenance or servicing, it becomes difficult and frustrating task to disassemble and then reassemble this whole thing. So the better approach is design it in this way. So all the bolts are accessible from the top. Yes, there are extra machining, the plate thickness increased, but now your design is optimized for assembly. So always try to optimize your design in a way that every bolted joint should be accessible without disturbing the other parts, without disturbing the other assembly. And also there should be enough space for the tools like Allen key or a spanner. Another example. Let's say you design a ball screw linear actuator. So standard bearing blocks usually comes with only bolted holes, no dowel holes. But the proper alignment between these two bearings is critical. So one way is manually align the bearing blocks during the assembly until you achieve a smooth motion. But the problem is once you disassemble it for the maintenance, maybe for changing the bearing block, you have to repeat the same alignment process again. And this makes the user or customer deeply disappointed. So better solution is add simple locating feature like a key on one side of each block. So every time you assemble, alignment is already defined, no trial and error. Now let's say your part is optimized for the manufacturing and assembly. But what about strength? I'm not talking about strength calculation or FE analysis, which comes later, but just about the geometry. Is your geometry optimized for strength? For example, in this pneumatic cylinder mounting bracket, if you joint the plate like this, the load from the cylinder will put the bolt in shear. And we all know the bolt shear strength is way lower than tensile strength. So why not just join the plate in this way? So the bolt will be loaded with the tension instead of shear. And if the load is higher, instead of simply increasing the plate thicknesses, you can add the ribs like that. This increases stiffness and strength. Also just remove this unnecessary fillet. Now let's take another example. Say you have a high torque drive shaft of 60 mm diameter supported by bearings, and now you need to connect a coupling of diameter only 10 mm. So if you directly reduce the shaft diameter from 60 mm to 10 mm in one single step for the coupling, it will create a very high stress concentration at that step, and that becomes a critical failure point. So a better approach is add a proper fillet or chamfer at the transition. An even better approach is reduce the diameter in multiple steps. This helps in distributing the stress more gradually, reduce the stress concentration. At the same time, it also makes the manufacturing part easier and more controlled. Now also take some sheet metal examples. If you're designing a flat sheet, it can buckle. So instead, you can add some curvature or waviness or weld some ribs. You will find this design technique in standard products. And to strengthen the edges, use hemming. It also removes the sharp edge problems. So the idea of design for strength is to achieve the maximum strength at minimum material and its weight. So this was essential DFMA. Design for manufacturing, design for assembly, and also design for strength. But our design should be also optimized for material, environment, and aesthetics. So next video should be on your screen where I have talked about more advanced DFMA. If you found this video useful, please give us a like. If you found this video useful, please give us a like or hype. And thank you so much for watching this video.